We now wish to consolidate the lessons from the last couple of lectures by looking at a real example. We will use the two data sets in this real example, both drawn from the same sensor. The first, at the top, is a 4-band set where the bands are spaced over the spectral range. The first two are in the yellow part of the spectrum, the third is in the near infrared, and the fourth is in the middle infrared. This dataset has a low degree of correlation. In the second dataset, at the bottom, we have intentionally chosen 4 wavebands close together in the near infrared range. This dataset has a high degree of correlation. You can tell that by inspection because the bands all look the same. In each case, we also show a color composite image product created using the band color combinations shown under the color product. The color composite for the correlated dataset is not very colorful, whereas that for the low correlation dataset is colorful. The color very much helps us pick out details among the cover types as we have come to expect from color image products. Now let's examine the principal components for the first of those datasets, that is, the one which shows low correlation. This slide shows the computed eigenvalues of the covariance matrix and the eigenvectors, here displayed by row, so that we can see which eigenvector corresponds to which eigenvalue. For all of these examples, the images have been contrast enhanced separately, otherwise the later principal components might all appear black. Note that even though the eigenvalues show rapidly decreasing variances, the components PC2, PC3 and PC4 still show a lot of detail, such that when the second and third principal components are used with the first to create a color product, a fairly colorful result occurs. Compared with the original color composite of the scene, there is a little more detail evident in the PC color composite than that formed from the original bands. Now look at the principal components of the second highly correlated dataset. Here we see a much more rapid drop-off in the eigenvalues, telling us that most variance is in the first principal component, which is what we see when looking at the PC images. Again, the second, third and fourth components would be too dark to view if they were not individually contrast enhanced. However, don't overlook the fact that while their variances might be almost negligible, there can be significant detail in later PC images. Look at the row of buildings in PC4, for example. In this case, the color composite formed from the first 3 principal components shows significant detail not evident in the color composite formed from the original bands. Note especially the lime green areas in the upper right-hand side of the image and several of the buildings down the left-hand side. Here we compare the 2 principal components sets on one slide. Note especially the different drop-off in the eigenvalues, the more apparent detail in the PCs in the top case, meaning the variance for that image is more shared among the PCs, compared with the bottom, in which the variance is highly compressed towards the earlier principal components. Note also how PC2 and PC4 in the second case seem to highlight particular features. This is the same set of PC images as on the previous slide. By looking at the color composite comparison, we note that there will generally be a more highly colored product from the PCs if the original dataset has low correlation among the bands. Another thing to note in both cases is that colors appear in the PC color composites that we almost never see in the color composites formed from the original data. Lime green and bright purple are examples. That is a direct result of removing the correlations, and we will explore that more later in our course. This slide puts it all together, so you can see the comparison between the two examples directly. The general conclusion we should draw is that if the bands of an image dataset are not strongly correlated to start with, then computing the principal components images will not achieve a great deal. There will always be some visual effect, unless there is absolutely no correlation in the original data. But in general, the more correlation there is among the original bands, the greater will be the effect of principal components analysis. This can definitely be seen in the second example. Computing PCs gives a much better colour result, for example, than with the original data. This slide allows you to see the original data and the principal components for both examples. Note that you can get an idea of the correlation among the bands just by looking at them. In the first example, they look different from each other and thus exhibit low correlation. In the second example, in the third row, they almost all look the same. That is why the colour composite looks almost monotone. It is in cases like this that principal components has the greatest effect. Two important points emerge in this summary. First, even though later principal components may contain very little variance, they may nevertheless contain some interesting detail that is quite different from the rest of the image. Secondly, we get much better use of colour with principal components imagery than with the original data. These questions stress the importance of the actual values of the eigenvalues and eigenvectors of the covariance matrix.